Cool. I'm very glad to see everyone here. I'm honored to present this what's new in RLlib 2.0 talk on behalf of the RL team. My name is Jun. I've been working on RLlib for almost a year now. I joined Anyskill last September. Also, Avnish and Sven is also here. They can help with the questions. For this particular talk, I want to leave enough time at the end because gathering feedback from the community is actually super important for the team and for us. Cool. All right, so today I'm going to talk about quite a few things that we spent a lot of time on in the last 3 to 6 months, leading to this 2.0 push. These are the things. Actually, like once we roll the slides, I noticed a common theme to these changes, which is to help improve the usability and extensibility of the RLlib framework, so that everyone has easier time to maintain and extend and use it, including ourselves actually. While the community and the use cases grow, like one of the pressing issue that we face is how to scale up the support and how to scale up the the functionality of the framework while not like overwhelming us on the maintenance work. Cool. So the very first thing I'm going to talk about is one of my favorite, which is the algorithm config feature. We probably spent maybe a quarter of time, and we actually get back one step. So if you've used RLlib, you have probably dealt with this thing called configuration dictionary, right? It's like a flat dictionary with like 200 configuration fields in there, and everyone's got like really confused about that, and it's really hard to spot like any specific things that you put in there. Personally, I've wasted maybe hour and a half on a problem I got really confused with, but actually I just set like the configuration bit to the string fos instead of the fos, and it turns out to be true, like in the algorithm, and I got really pissed about that. So this specific feature that we introduced is to introduce semantic meaning to all these, like the flat list of configuration bits, and also we try to group the things together a little bit better so that it's super easy for everyone to like find the stuff. And as you can see on this slide, this is the old days of how you're gonna like configure a RLlib trainer. And going forward, this is how you do that. From the left-hand side of the scripts, you see that we import this thing called PPO configuration. Instead of a Python dictionary, it's actually a data class object now. And you initialize this thing, and you call like training environments, resource on those, and you can actually chain all these configurations together, which actually makes things much clearer. And at the end of this configuration, you can even like simply call build function on this configuration object, and you're gonna get like a PPO trainer back, which previously you will have to do like PPO and then configure equal to some dictionary. Yeah, I just like this feature a lot personally because this introduced a lot of like order into this total chaos of configurations. Okay, so this is one thing, and the second thing is probably the project that we as a team spend most of the amount of time on the last 2 quarters. So configuration object is mostly for this off-the-shelf use case, right? But now, if you want to customize and extend the library of algorithms in RLlib, historically what you will have to do is to write a algorithm with this execution plan. And you can think of this execution plan as like a TF1 like static graph definition, where the RLlib team actually provides you with these primitive operations, like for example, parallel rollouts, concatenate the batches together, and we do this training step, and then we do metrics reporting and weight synchronization. It actually has its upside. For example, these operations are written by the RLlib team. They are like super optimized. So in terms of like efficiency and stuff, they may be a little better. But the downside is also very obvious. The downside is so that extending the library of operation becomes like much harder, because you will have to go write this operation first, and then you want to use this in the algorithm. And also, the most mind-twisting part is this function actually only gets run once, right? When the algorithm is constructed. Once the computation graph is done, during the actual training, what gets executed is the production from this function. It's like the computation graph that gets executed. So that makes it super hard to step through the algorithm to debug it, for example. And if you have anything and you want to stop and just inspect the data, you'd have to actually write a operation, add this in the computation graph. It's much like the TF print thing. I'm not sure if you guys know that, but it's basically the same idea. So similar to how TF1 is like gradually getting dominated more by PyTorch. What we are trying to do here is to also introduce a natural way of writing these algorithms. The goal we are trying to achieve is to so that the algorithm's training step actually looks like the pseudocode that you see in all these like reinforcement learning papers, right? Usually these pseudocoders are very short, very concise, like a few steps. We want to make it so that you can easily translate those into the algorithm and make it a new RL algorithm. So this is what we have today. We actually spend maybe like almost a quarter, and Avnish personally dedicated a lot of hours on translating all our algorithms to implement them again in this pattern. So what we have today is these are all simple function calls, right? What you see is like for this very simple policy gradient training step, you have a function call to like parallelly, asynchronously fan out to all the rollout workers, collect the sample batch, concatenate them, and feed it into the multi-GPU trainer, which you run by calling this multi-GPU trainer train one step. And then after the training step is done, you call the sync weight function to send the updated weight to all the rollout workers, right? And this becomes like a much natural-looking implementation than the old execution plan. We did this actually based on a lot of the user feedbacks actually from you guys. We hope this is like much easier to work with, going forward. Cool. So that's the second thing that we should expect. The third thing is called the subclassing implementation. I don't know if you guys remember, like historically, RLlib has been using these like builder pattern, and we literally like have this comment in the code base saying, you guys should not like just inherit this directly. Please use the build trainer and build policy function to do this, right? It's basically like a bunch of templates with a set of extension points, and you can replace those extension points by providing overriding functions here. It's actually just not very like for one, it's not super clear because to figure out what the policy actually looks like, you need to go look at the template class, and then you need to look at what's getting overridden here. And also, because the set of extension points are fixed, making modification, making like extension change that's not covered by the current set of extension points is harder because you need to make a framework change, right? And then you can like use those in the builder function. So I'm not sure if you guys remember, but for this build policy class thing, we used to have these parameters called like before init, before last init, like after init, after last init. Like that looks crazy, totally weird. So we thought like, also based on user feedback, we thought like, let's get rid of that, and we should just use like the simple Python inheritance to implement all these classes. Okay, so and just for as an example, these are what the algorithm and policy class look like today, right? I think we've converted all the algorithms to be in this format. I think we still have a couple policies that's not fully migrated yet, but the goal is so that you can easily extend a PPO algorithm, for example, from the base algorithm, and you just override the APIs that you want. And because of this, you can actually use the base implementation a lot more easier, because you can just call into like super the base version of the API. And if you want to make change to these init functions, you can feel free to just arrange things however you want instead of trying to fit things into this before some step, after some step pattern. One additional thing I want to mention is we used to have this list of mixed things that seems like a little weird because it sort of changes, completely modifies the behavior of a class without it seems like pretty magical. Like you just specify this mixing and some behavior gets modified somewhere. In this new world, actually, what we have is we are using these mixings as like in the base class list. So you can clearly see, this PPO torch policy is built on top of these like building blocks: value network, target network, learning rate schedule, and then at the end there's like the base torch policy. Okay, so this is the idea of subclassing. So the first thing I want to share is about this thing called a connector. It's right now, it's in 2.0, and it's in disabled by default state. So if you guys want to try it out, you guys can feel free to do that. So the idea about connector is this. Like if you go to our GitHub or our discussion forum, one of the most common questions we get is basically, like people ask, what do we do about this, training? Once the training done, like what do I do with this checkpoint? Like how do I serve it? How do I use it in production, right? Historically, I think the library and even like the entire field focuses on more research use case a little more than the production use case. So the reason it wasn't handled very well before was because the user provides the environment, and RLlib provides this neural network training functionality, right? But there's like a lot of like pre-processing and post-processing that's happening inside the framework. Actually, it happens like throughout the framework. Sometimes at some random places that that is not very intuitive. So if you do that, then the only way for you to use the checkpoint is also to grab the entire training framework, plug your environment in, and hopefully you will get the same computation in serving and inference. So that's clearly very problematic because that made people very reluctant to upgrade RLlib version, because every time you upgrade, that means the old policies you've trained becomes obsolete. Like you basically cannot restore those anymore. And also, a lot of feedbacks we got from the users is basically people's environment actually is not usually not static, right? They also go through multiple iterations of change, over time. So while training these policies are super expensive, they spend a lot of money and computation power on these policy. They want the shelf life of these policy to be much longer than the upgrade cycle of RLlib, which usually is monthly. So so that's why we come up with this connector concept. Basically, what connector does is we're trying to consolidate all these pre-processing and the post-processing steps between the policy and the environment into a single framework. And these computations actually are checkpointed with the policy, right? If you do that, that means you can recover a policy and use it without recovering the old training stack that you used to train these policies. That allows you to do things like just straight recover a policy checkpoint from a policy file. For example, this middle graph shows, in the new world, you will be able to just provide a checkpoint path, and then we're going to recover a policy for you, and you can just do local policy inference on that. And it also allows you to do things in case your environment is different. You can actually now come in and modify the chain of connectors that you used for this policy so that you can adapt the new environment to make the data work with the old policy. So that's the main idea. We have some more advanced usage of this plan in the future. For example, remote inferencing and all that stuff. But feel free to give this a try and see if that makes your post-training life easier, and give us feedback. Okay. So the last thing I want to talk about that's in 2.0 is this error integration. So rate error is actually a pretty big topic for rate 2.0. It has a strong focus on, for example, scalable data ingestion, and it has a strong focus on unified APIs throughout the libraries. While RL doesn't fit the framework that much, we have built reasonable, preliminary integration with rate error for all these offline methods. For example, now dataset is a first-class input thing that you can use with RLlib. That allows you to do offline training with a very large-scale dataset. You can actually do distributed ingestion as well. And RLlib is using the same checkpoint format as all the other AI library. The benefit of that is then once you get a checkpoint, you can easily use a AI predictor to recover and start serving these RL policies. So I'm showing an example of the RL trainer here. Apologize, the example is written before the algorithm config project was completed, so it still used the old configure dictionary. But you can see that the key idea is that once you create this trainer, you have the same .fit API that you can use to train the RL policy. And once you have the result, you can actually easily recover the checkpoint and use it in a batch predictor kind of way, which is the predictor predict. So expect more integration to happen in the coming months. But this is our integration so far. Yeah. Cool. So so just to give you guys a very quick idea about a few of the major biggest changes that we're bringing to you guys with the 2.0 release. I want to emphasize here that the RL team is actually still very small and very nimble and super motivated to make it work for the open source and the AnyScale communities. So please do give feedback, and we usually resource permitting, we'll try to try to make everyone happy, basically. Cool. So I intentionally leave a little more time for this talk so that people can chime in and we can discuss some of the pros and cons and changes and stuff. And Sven and Avnish can actually help with the questions. Okay.
All right. If you guys have questions, raise your hand and I'll bring you the mic.
So the question on the new update on configuration, because in our team we actually make use of the configuration like dictionary, make it as a YAML file to configure our training experience.
I see.
And we actually make it scalable because we can actually have different version of the configuration file, and that we can actually leverage that to set up different trainer and different version of trainer so we can train different version of policies. So my question would be, because we still want to leverage our workflow. Is it possible in RLlib 2.0 we still can able to like initialize the trainer with a config file?
Yeah, totally. It's still supported. So this configuration object thing is like a layer on top of the dict. Actually, at the end it gets compiled down to this dictionary still. It just has a lot of like validation and types checking things built into this. So it's a lot safer way to build this dictionary. But if you already have like a YAML file that have like all these configurations specified, it will still work. Yeah.
Okay, that's good.
And there's no plan to like get rid of that.
Okay, that's good.
Yeah. In fact, like the internal testing stuff that we have also relies on YAML, which I don't know. Yeah.
So currently it's in a state where you have the config object and everything gets converted to a dict for now, and the algorithm still works with a dict.
Okay.
Where we want to get is that you have the YAML file and you convert that into a config object, and then the algorithm will work only with the config object.
Yeah.
But we're not there. This is just really on the surface right now.
Okay, cool. Good to know that.
But everything still works, and it will continue to work with the YAML files. Yeah.
Another question I have is regarding to the checkpoint store, because checkpoint restore. I was like, I'm not so clear about because you mentioned about different version of way, checkpoint train from different versions. Yeah, checkpoint train from different version of way.
Yeah.
You can still restore and then run, despite the change on the way, code base, or even the environment. That's something I want to ask more detail.
Right.
Because the environment constantly can change because of different
Exactly.
updating.
So we did a connector project specifically for this pain point where people's environment actually evolve over time. So their policy basically becomes like useless after. So there's a way to you can wrap the environment, right? If you're only working with like a single policy that you train from the RLlib, you can always just wrap the environment to make it work with the policy. But there are use cases where people will have multiple versions, like people will have multiple policies trained with multiple versions of the environment and multiple versions of the RLlib, and they try to make them work together. For example, in the context of evaluation, right? You want to train a new policy and play it against some old policies that you've trained. So for those use cases, actually, that's actually why we introduced a connector where the policy checkpoint is by itself very like self-contained and separate from the training side of things, right? If you think about checkpoint, checkpoint is mostly used for two purposes. One is for fault tolerance. Like if your training stack goes down, you can bring them back up and using the checkpoint to resume from the training. Another purpose is to, after the training is done, you can get the policy out of the checkpoint and use that for serving. So unfortunately, these two use cases are mixed together today with the same checkpoint concept. But we're trying to use connector to kind of separate them a little bit so that the policy is self-contained. It contains all the computations and configurations and the weights and stuff that's like required if you want to run the policy. Okay. And then in inference, not for fault tolerance, for the inference use case, you can also only grab the policy part of the checkpoint and reinstate that. And because you don't need to do training of that, we don't need to like save any training related state with the checkpoint, which means any change to the training side of the code base is not going to affect the checkpoint, right? So the checkpoint becomes like a lot more durable, basically, because of that. And I think actually it also enables. I think it also enables people to do for things like stateless like deployment of the policy, and the stateful part you can move to the client side using connector, and they'll talk to some like centralized serve deployment, which is just do neural network forward pass. Yeah.
Hey, so in the past, when we've used RLlib to train a model, we generally export it to Onyx, so it could be inference and served elsewhere. Part of the problem that we had in the past is some of these Onyx runtimes that need to be able to load this model need extra metadata put into the model so that it can understand it. In the past, we pretty much just forked the repo and had to hack in whatever we needed to do. But now that I see that you guys can actually inherit the objects and possibly change it, have the work that you guys been done to that extent where we can actually add stuff to the PyTorch model and expect it to be exported as well?
So I think the work I described in this talk is more geared towards like you train something and you still want to use RLlib to serve it. If you're trying to write things into Onyx, I assume you're trying to like just run this model independently, like by itself, or
Like
somehow.
in Unity or something like that.
Yeah, exactly. So for that specific use case, there are work planned for you to. Actually, specifically for gaming, I think there are a lot of use cases where people want to run the model, not even not in Python, right? In some other languages. I'll recommend you stay tuned. There are work plans that will make those a lot easier. The model structure, the weights, and the metadata will allow you to write like from some API that we're still yet to decide it. But we should allow people to like explore things that way. Okay. But I want to warn you that connector actually solves a lot of the like it remembers all these processing computation for you, right, between the thing. So if you export the model that way, you will need to handle that part, like all the flattening, for example, like all the like one hot or frame skipping and all that stuff. Like you will have to write yourself. Yeah.
Any question here?
Yeah, actually, just maybe add to the use case so that the voice is a bit stronger. Yesterday, I spent a couple hours while trying to export the model for C++ code, and I was a little bit confused because the trainer inference was different than the policy inference because the trainer was clipping the actions and whatnot. So, so things like that sometimes.
Exactly. That's actually exactly the issue I was talking about. Sometimes like the modification happens in some places that's like not very intuitive and weird.
Yeah, it would be pretty nice to have them in the graph itself. But
exactly. So my goal is trying to like consolidate all of them into like connector, right? So you can expect there's going to be like a action clipping, connector that's doing that. If you disable action clipping connector, then you don't have action clipping in the post-processing. Yeah.
Okay, we have time for maybe one or two more quick questions. All right, we can wrap it up then. Thank you so much, June.
All right.